All right, fire up those compilers, everyone, because we are going deep, deep into the world of C programming today.
Deep dive is right. This isn't just some surface level stuff.
They're going full-on scuba gear, diving into the depths of these university-level lecture scripts on C.
And let me tell you, these excerpts are no walk in the park. They cover the whole shebang, starting with C's origin story.
Which, spoiler alert, involves those Bell Labs geniuses back in the 70s, right?
You got it. Bell Labs, the birthplace of Unix. C was right there in the thick of it.
A real blast from the past. But why should we care about a language that's older than, well, me?
Because, and this is key, C is the ultimate optimizer. It's all about efficiency.
Okay, so we're talking about writing super fast code, right?
Exactly. Think about those massive scientific simulations that can take days, even weeks to run. C can cut that time down significantly.
So it's like trading your bicycle for a sports car.
More like trading your horse and buggy for a jet plane. But here's the thing. C isn't just about raw speed.
It's about understanding how software talks directly to the hardware, the nuts and bolts of it all.
Exactly. And that's where data types come in. This is where things get interesting.
Data types, those sound kind of, well, dry.
They might sound a bit technical, but trust me, they're the heart and soul of C. Think of data types as the way you communicate with the computer about what kind of information you're dealing with.
Like giving the computer a heads up.
Exactly. You're telling it, hey, this is a number, this is a letter, this is a whole sentence.
Makes sense. You wouldn't want to mix those up.
Exactly. And the lecture script does a great job of explaining the core data types, starting with integers, those numerical workhorses we use for counting. But here's where it gets even cooler. There's this important distinction between signed and unsigned integers.
Signed versus unsigned. Okay, now you've got my attention.
Think of it like this. A signed integer is like a bank account balance. It can go positive or negative. An unsigned integer, on the other hand, is like the number of jelly beans in a jar.
You can't have negative jelly beans.
Precisely. The lecture script really hammers home this point about choosing the right data type for the job.
So it's not just about getting the code to run, it's about making sure it runs correctly.
And that it doesn't crash your entire system. Now, besides integers, we've also got those ever-important floating point numbers.
Ah, yes, the decimals. For when whole numbers just won't cut it.
Exactly. Floating point numbers are crucial for anything involving fractions, like calculating the trajectory of a rocket.
Or figuring out the exact amount of fuel a plane needs for a long-haul flight.
Exactly. Every decimal point matters in those situations.
Yeah, can't argue with that.
And then we have characters. Now, these might seem pretty basic, but they're how we represent letters, symbols, punctuation, you name it. It's how we communicate with computers using human-readable text.
Because deep down, computers only speak in ones and neos, right?
Exactly. Characters are our way of translating between our world and the computer's binary world.
It's like deciphering a secret code. But once we've got our data types all sorted out, how do we actually turn this C code into something the computer can understand and execute? I mean, it's not like we're just handing the computer a to-do list, right?
You're right. It's not that simple. That's where this whole process of compilation comes in.
Compilation. Sounds kind of intense.
It's a bit like translating a recipe from a foreign language into something the computer can actually cook, or in this case, execute.
More like deciphering ancient hieroglyphics, I'd imagine.
Well, it can feel that way sometimes. But these lecture excerpts do a good job of breaking down the key steps involved. You've got your pre-processing, your compiling, your linking. Each step plays a crucial role in turning that human-readable C code into something the machine can actually process.
So it's not just a one-and-done kind of deal.
Not at all. It's a whole chain reaction happening behind the scenes.
Fascinating stuff. But what happens if something goes wrong during this compilation process? Are there any red flags we should be on the lookout for?
That's a great question. And as luck would have it, these lecture excerpts delve into those potential coding catastrophes known as overflows and underflows.
Overflows, underflows, those sound ominous.
They can be, believe me. Yeah, picture this. You've got this tiny little box, right? And you're trying to cram a giant oversized package inside. Something's got to give, right?
It's going to explode.
Well, in the world of code, that's an overflow. You're trying to stuff a value that's way too big into a data type that's just too small to handle it.
And I'm guessing an underflow is like using a telescope to measure the thickness of a sheet of paper. Your tool's just not designed for that level of detail.
Perfect analogy. You're trying to squeeze an incredible amount of precision into a data type that just can't handle it. And let me tell you, these overflows and underflows, they can wreak havoc on your code.
We're talking system crashes, security vulnerabilities, the whole 9 yards.
You got it. especially when you think about software that's controlling critical systems. Airplanes, medical devices, self-driving cars.
Even a tiny error could have catastrophic consequences.
Exactly. So you gotta be really careful with those data types. But you know what else helps prevent these kinds of coding calamities?
Hit me with it.
Functions. They're like the unsung heroes of good code. The lecture script actually spends a good chunk of time on functions, and for good reason.
Okay, so we're shifting gears from potential disasters to the organizational saviors of our code. Tell me more about these functions. What makes them so special?
Think of functions like building blocks. Imagine you're putting together a giant Lego masterpiece.
I'm with you.
You wouldn't create each individual brick from scratch, would you?
That would take forever.
Exactly. Functions are like those pre-made Lego pieces. They represent a specific task or calculation.
So you can create a function to, say, calculate the area of a circle, and then just reuse that function anywhere in your code.
You got it. It's all about modularity and reusability. The lecture script even walks us through a simple add two numbers function as an example.
Same and simple, right?
Exactly. It breaks down how functions take input, process it according to a set of instructions, and then return a result.
And once you got that function built, you can call upon it whenever you need to perform that specific task.
Exactly. It's like having a team of specialized robots ready to execute your every command.
I like the way you think. But let's say we've got our code neatly organized with all these helpful functions. How do we actually control the flow of our program? It's not like we're just giving the computer one giant to-do list to follow line by line, are we?
Great question. And you're right, it's not that linear. That's where control structures come in. They're like the traffic signals and roundabouts of your code, directing the flow of execution based on certain conditions.
Okay, now we're talking. Control structures. Are these where things get really interesting?
You bet. The lecture script focuses on two main types: conditional statements and loops. Conditional statements are all about decision-making.
Like those choose-your-own-adventure books we used to read as kids.
Exactly. You're giving the program different paths to take based on certain conditions. Imagine you're writing a program to determine if someone's eligible for a discount.
Like a senior discount at the movie theater.
Precisely. You'd use an if statement to check the customer's age. If they're 65 or older, they get the discount. Else, they'll have to pay full price.
It's like giving the computer a set of rules to follow.
Exactly. And then we have loops, which are perfect for when you need to repeat a certain task multiple times. Think of a for loop, like setting a timer on your oven.
You tell it how many times to run, and it stops automatically when the timer goes off.
Exactly. So if you wanted to print all the numbers from 1 to 100, a for loop would be the way to go.
Makes sense. What about while loops? How are those different?
A while loop is more like saying, keep doing this task while a certain condition is true.
It's like checking to see if your coffee's reached the perfect temperature. You keep checking while it's too cold, and once it's just right, you stop.
That's a great way to put it. The lecture script gives some good examples of how to use both for loops and while loops in C.
So it's all about choosing the right loop for the job. So with these control structures, we can make our C programs really smart. But this has been quite a journey. We've covered so much ground, from the birth of C at Bell Labs to this intricate world of data types, functions, and now these powerful control structures.
And you know, what's amazing is that these aren't just abstract concepts. This is knowledge you can actually use. C might be an older language, but its influence is everywhere.
It's the foundation of so much of the technology we use every day.
Exactly. And the principles we've talked about, they underpin so many other programming languages as well.
So it's like learning the secret handshake that grants you entry into this whole other world.
Exactly. And who knows, maybe this deep dive will inspire someone out there to write the next great operating system or create an app that changes the world.
The possibilities are endless once you unlock the power of C. And on that note, we'll wrap up this deep dive into the world of C programming. Big thanks to our expert for joining us and sharing their insights.
It's been my pleasure.
And to all our listeners out there, keep those compilers fired up, and we'll catch you in the next deep dive.